Hello, ATS 570 students. This is Dr. John Schrage, and this is a follow-up to our lecture that we had the other day about filtering. This is a lecture in which we're going to talk about some of the properties of filters. In class the other day, we talked about one main type of filter, the Lanczos filter, just named after the scientist who invented it. And there are actually a whole bunch of different types of filters: the Butterworth filter, the Murakami filter, the binomial filter, sorry, as well as things like uh, running means, which are also sort of a type of filter. And unsurprisingly, there are pros and cons to using different types of filters, as well as, of course, remember one of the parameters you had to choose on the filter was K, the half window size, where 2K plus 1 observations are included in the computation of the filtered observation at each point. And so based on these properties, there can these things that you choose and which filter you choose, your filter can have different properties. Now, just to review, don't forget that there are three main types of filters. Whether we're talking about Lanczos or Butterworth or Murakami or any of the other kinds of filters, they can be low pass, meaning that low frequency signals pass through the filter and are preserved, whereas high frequency stuff is removed. There are high pass filters in which the high frequency stuff is passed through the filter and preserved, whereas the low frequency stuff is removed. And then there's the band pass filters, where only the frequencies in a certain range are preserved, higher frequencies are removed, and lower frequencies are removed. It's easiest to envision this business of the different types of filters and their properties by thinking about a property that we call the filter response function. And we normally display the filter response function as a graph as a way to understand what it is doing. The y-axis of the graph of the filter response function is usually just labeled something like response or power, and it is going to be a number in the range. It should be in the range of 0 to 1, although you'll see that sometimes it gets a little bit outside of that range. And then on the x-axis of this diagram, we're going to have period or frequency. Most of the time in meteorology, we work in terms of periods, so that's how I have this diagram labeled. When you are working with this filter response function, you're going to need to know where on this x-axis your cutoff frequencies of your filter map to. So you typically will have decided, like for example, in the homework, I think you had to make a filter that was a low-pass filter that kept things with frequencies, with periods longer than 30 days. It was a low-pass filter. So you had some cutoff frequency associated with a period, in this case, I think it was 30 days. Now, ideally, if this was working perfectly, a low-pass filter would have a filter response function that would look something like this diagram right here. You would want the filter to have no response to, it would not pass any signals between a period of 0 days and your cutoff frequency, which we used as 30, corresponded to a period of 30 days. So you'd have zero response. Effectively, you're multiplying those frequencies, those oscillations by 0. And then there would be the step function that would go straight up to 1, where from your cutoff frequency and longer periods, lower frequencies, you'd have a frequency response of 1. Ideally, that would mean then that effectively you're multiplying those frequencies by 1, and you're keeping everything. You have this very square-looking function. You could see the same sort of thing for like a high-pass filter. Ideally, your high-pass filter would have a filter response function that looks something like this, where the range of frequencies you're trying to keep have a value of 1, in the sense that you are like effectively multiplying those frequencies by 1, and then for values of frequency or period that map to beyond 30 days, your cutoff frequency, they would be multiplied by 0. In this particular case, of course, too, keep in mind that for a bandpass filter where you have two cutoff frequencies, a low frequency cutoff and a high frequency cutoff, then your ideal filter response function would look like this, sort of a little boxcar function or a little square wave type function, where there's 0 response outside your frequency range and 100% response inside the frequency range. Okay, so what we're going to need is a way to actually compute the real frequency response function of each of the filters that we're creating, and that way we can take a look and see, does this filter that we're making have properties that we want for it? Does it respond correctly? Well, it's a fairly straightforward equation to compute the frequency response function of a filter. At any given frequency f, there is a frequency response. It's just a simple function here. You notice that it is just sort of a function of the weights of the filter. Notice we just use the filters, the weights from j equals 1 to j equals k. Effectively the ones beyond 0 on that list of weights that we created. And remember, we have weights like that for anything from a running mean to a Lanczos filter to whatever. So it's not a terribly difficult thing. Usually you have to then convert those frequencies back into periods. We don't normally make the graph in terms of frequency. And so you get a graph that looks something like this. Now, for the assignment today, you needed to create a pass Lanczos filter. It had 121 weights. K was equal to 60 and had a cutoff frequency at 6 months and at 30 months. And your filter worked nice. It looked beautiful. It had certain properties. But I mean, it did a good job of removing higher frequency and low frequency stuff. And here's what its filter response function looks like. Now, if we actually could map here where our high and low frequency cutoffs are, you would see that they're right there at 6 months and at 30 months. And these cutoff periods turn out to actually be where the frequency response function hits 0.5 or 50%. Ideally, it would be a square function. Right there, it would be jumping directly from 0 to 1, but in fact, that's just where it crosses 0.5. Now, on the left side there of mapping 6 days, you can see the Lanczos filter actually that's pretty good. That looks pretty much like a square step function, but not so much on the right side of the function here, where it sort of tapers rather than having the right properties of just a step. Now, if you had known that you had a frequency that was, a filter rather, that was cutting off between 6 and 30 months, you would have been rightly thinking that, well, then if you had some process in that data set that was happening on 25 months timescales, it should have passed through there unharmed. You should still be able to see that. But in fact, you can see that if you look on your diagram here, at 25 months, well, you don't have 100% response. The function is actually, the filter is actually removing some things at a period of 25 months. In fact, just to kind of demonstrate it here, I made this little sample test here where the blue curve is actually a sine wave with a period of 25 months. It's perfect, it's exact, it's mathematical, it has a period of exactly 25 months, and then I applied this filter. Well, with a name like 6 to 30 month filter, you'd assume it would have been preserved, but in fact, if you look at the purple curve, which is the filter data, you see that it has sort of been lost. Don't get me wrong, it still looks mostly like the original sine wave, but gee, you thought it was going to actually pass through unharmed, and it didn't. Worse yet, there are some frequencies where the frequency response function actually is slightly more than 100%. If you actually take a look here, I just zoomed in real tight on the frequency response function. Right around 21, 22 days, the frequency response is slightly greater than 1. Now, as you're going to see, this is by no means the worst example of that problem, but it did get to be slightly more than 1, and actually somewhere near 21 and a half days, 21 and a half months rather, we had a peak slightly higher than 1, which means that our filter won't just preserve those oscillations, it'll actually exaggerate them. So here I just made on blue here, I made a sine wave that had a period of 21 and a half months on there, and the purple is the filter, and it's a little hard to see unless you zoom in, but the purple is slightly exaggerated. It has slightly inflated the values of the purple curve rather than preserving them. Again, that's not entirely what we wanted this curve to be like. Perhaps even worse, there's some frequencies where the response is less than 0. I apologize, the slide says more than 0, but it's less than 0. In fact, if we zoom in on the diagram here, out near like 48, 49 months, again, a region where you would have thought the response would be 0, in fact, the frequency response is less than 0. That means if I feed it a sine wave with a period of, say, 50 months, which should just filter out and leave nothing but 0 behind, you see with the purple curve there that we actually not only get a little bit of signal through, but it's actually the opposite of the real signal. It actually, it's like we're multiplying the real signal by a number slightly less than 0. Again, it's a little hard to see unless we zoom in, but there's a real problem here. The real values there is a little bit of signal here. Now, to some extent, I'm sort of making a mountain out of a molehill here. I mean, for the business of some frequencies having responses that are greater or less than 100% or 0%, well, frankly, there's a reason why we use the Lanczos filter. It isn't, frankly, all that bad. In contrast, let me show you the frequency response function for a filter other than the Lanczos filter. I can't remember. I think this is the Murakami filter, but it doesn't really matter. But notice, oh my goodness, it's kind of a disaster. I mean, it has lots of frequencies in which the frequency response function in our bandpass, or actually in this case it's a high well, actually this is a low pass because it's in terms of frequency, but whatever. You can see we have several places where it's much more than 1, and several places where it's quite a bit lower than 0. Plenty of places where it should be 0, where it's actually small positive numbers. This is a disaster. This filter, it's useful for certain purposes. It has certain properties that Lanczos filters don't, but this particular filter is not very useful in atmospheric sciences. And speaking of filters that are a bit of a disaster, here's what the filter response function for a 9-month running mean looks like. You might remember a couple assignments ago we did a 9-month running mean of data, and if you take those weights, remember we could think of a filter as having of a running mean as having weights. This is what the filter response function looks like. Well, this isn't anything what you were hoping it would look like. This is why I told you that running means are a poor example of how to filter data. I mean, if I set this frequency response function next to an example of a Lanczos frequency response function, you can see that they do have what are called Gibbs oscillations, these little wiggles near the cutoff frequencies, but clearly the problem is much worse for the running mean. They have unexpected behaviors near the frequency cutoff frequencies, but they just are, the one for the running mean is near 0. I mean, notice, for example, at the cutoff frequency of 9 months, cutoff period of 9 months for the running mean, you actually have 0 response there. It's one of the few places you have actually 0 response. Running means just have strange properties when it comes to their frequency response function. Still, this frequency response function that we have for the Lanczos filter, though, it's just not that bad. I mean, if I just sort of put it next to its step function, it's clear that it's hardly the end of the world. It's not just too bad. Could we make it better? Well, what if we chose fewer weights? That was k equals 60, so we had 121 weights. What if we chose k equals 10? Wow, there's its frequency response function. It's just terrible. It clearly doesn't look anything like a step. Well, what if we chose more weights? Well, that's better. Now I have k equals 100 instead of k equals 60, so now we're using 201 data points to compute each filtered observation. Well, it doesn't seem just too bad. On the other hand, there's quite a trade-off here, right? We're throwing away a lot more data because you can't use the data for the first k and last k observations. I mean, the larger we make the value of k, we do get closer and closer to a true step function. The problem is we're throwing away too much data at the beginning and the ending of the time series. Okay, now that you've seen this, let me just sort of breeze through how to do this on today's assignment. I'd recommend just getting this PowerPoint so you can see the details of this better. YouTube is not necessarily the best format for that. What I want you to understand is you're going to have two spreadsheets. One is going to be called Lanczos Bandpass Filter Weight Generator.excel sheet, and one is called Filter Response Function Excel spreadsheet. And what you're going to do is you're going to use these spreadsheets to generate values that you're going to cut and paste onto your own. So here's an example of what you'll see in the Lanczos Bandpass Filter Weight Generator spreadsheet. And here's what you see when you look at the Filter Response Function generator. So what you're going to need to do is you need to go over to your filter response function generator, and you have to fill that that yellow range in there with zeros, and then go back to your Lanczos Bandpass Filter Weight Generator spreadsheet and compute all the weights of your Lanczos filter by setting the different weights and the values of k and so on. Then what you do is you just go and you select the weights from j equals 0 to j equals k and hit copy. Go back to your filter response generator and spreadsheet and go to that first yellow cell, and then you're going to choose Edit, Paste Special Values Transpose. And if that works, that will fill in the whole mess of calculations and it'll compute the response function for you. If you scroll over to the left side of the spreadsheet, you'll see that there's a graph of the filter response function for you working there, and make sure it looks like what you think it should. All right, then, depending on the questions that you're working on, you may need to copy certain values from these spreadsheets over to a new spreadsheet and do things with them. You can use the same process, this filter response function Excel spreadsheet, to compute the filter response function for a running mean as well. Just set all the weights to 0, and then set the weights that are from j equals 1 to j equals k to the value 1 over 2k plus 1. I believe that's correct. And you should get the same response function, but just for running means rather than for a filter. Again, actually reading that stuff off the spreadsheet, off the PowerPoint will probably work better than in YouTube. Anyway, if you have any questions, please let me know. This has been Dr. John Schrage.